related rates. We're first going to discuss strategy for related rates problems, and then we'll look at some examples. But first, how do we know we're dealing with a related rates problem? So these are going to be application problems where we have two or more quantities that are dependent on each other and are changing over the course of time. So if you identify a word problem where you notice that two things or perhaps more are changing over the course of time and have some sort of a relationship, you're dealing with a related rates problem. So how do we approach these problems? Well, the first thing you'd want to look at is, do you even understand what the problem is asking? So make sure you understand the problem. And what we mean by that is we want to know, what are we looking for? So what are we trying to find? And some other things we might want to pay attention to is what remains constant in the problem and what varies. So what quantities remain constant and which ones change? So once we've understood those different aspects of the problem, the next thing that you may want to do, in some cases this is an unnecessary step, but a lot of times this does help, is develop some sort of a mathematical model. Meaning, draw a picture if you have to. Once we have our picture, if we would like one, we're going to move on to trying to determine what equation will relate all of these quantities. So find or write an equation What type of equation are we going to be looking at? Well, oftentimes you're going to be dealing with geometric equations, trigonometric equations. So look out for things like volume or area formulas. So for example, volume, area. Maybe we have Pythagorean theorem. It's a common one. Maybe we're dealing with angles and sides of a right triangle, so we might want to utilize trig functions. So trig definitions. Remember, trig definitions are an equation themselves. When I say sine of theta equals the opposite over the hypotenuse, that's actually an equation, so we can use that. So things like that, that's where you're looking to use, or what equations you're going to look to set up. Now, once we've discovered whatever equation we need, we then want to differentiate both sides implicitly with respect to time, okay? Now, I should say, actually, before we do the differentiation process, when we write the equation, let's add this in, and I think it's a useful thing to star. Once you've determined what equation you're using, ask yourself, are any of these variables within my equation remaining constant? If so, we can substitute in a constant value for that variable before we actually do that differentiation process. So let's add this in. Let's say determine at this point what variables remain constant and which ones change. And we should have already analyzed that in our first step. So at this point, once we've determined that, we're going to substitute in constant value where it's applicable. And the reason we'd want to do this at this point, before the differentiation process, is because taking the derivative of a constant is very easy. It just goes to 0. And it can also make our differentiation process much easier. I may take a product rule and reduce it down to just a constant multiple rule by just identifying that one of these variables remains constant. Now, if you forget to do this, it's not the end of the world. You'll just have to identify the rate of change of that variable that's supposed to remain constant is 0, and you'll have to substitute in at that point. But something that can make your life easier if you're able to remember that step. So once we've come up with the equation, we've substituted in constants for the variables that remain constant throughout the course of time, and we keep the ones that change as variables. We are now ready to actually do the differentiation. So we want to differentiate both sides implicitly. With respect to time. So this idea of implicit, and because it's with respect to time, that means we're going to have to use a chain rule on the variables that don't represent time, which is oftentimes all of them. So use, that bold. So don't forget that chain rule for this. Once we have differentiated, we are now ready to substitute in the values for whatever we need, whatever we were given. So if we have variables that have values at that point in time, we want to make our substitution. And once we've done that, we can then solve and interpret. So once you've solved for whatever you're looking for, whatever rate of change you're trying to find, interpret your solution. Make sure that you understand what your solution represents. If you're moving in a certain direction, so if you're dealing with movement and the value's positive, that will tell you a certain direction, but if it's negative, it'll tell you going in another direction. Make sure your labels are correct. If you're dealing with rates of change of volumes versus areas versus some linear measurement, make sure you pay attention to things like that. So now that we have our strategy, let's look at some examples. So our first question. The radius of a right circular cylinder is increasing at a rate of 5 inches per second, while the height is decreasing at a rate of 8 inches per second. At what rate is the volume of the cylinder changing when the radius is 15 inches and the height is 12 inches? So let's make sure we understand the problem. What are we trying to find? We are trying to determine at what rate is the volume of the cylinder changing. So when I see the term rate, I know I'm talking about a derivative, and I'm looking for the volume. So we want the rate of change of the volume with respect to time. So what else do we know? We have a radius of a right circular cylinder is increasing at a rate of 5 inches per second. So the radius rate of change is increasing. So if it's increasing, we want that value to be positive. So I know the rate of change of my radius with respect to time is a positive 5, while the height is decreasing at a rate of 8 inches per second. So we have decreasing now. So that means the value of the height is lowering, obviously. So the rate must be a negative value. So something to pay attention to. When you have values that are decreasing, make sure their rates of change are negative. Or if you have something that's in motion, make sure that you pay attention to what direction that thing is moving to determine whether or not your rate of change has to be a positive or negative number. So if something's moving down or if something's moving to the left, you're going to want to make that rate of change negative. So something to also pay attention to, which is very important in these related rates problems. So, that whole thing just moved on me. we're going to have a -8 here. So I think we've understood. So we want at the time when r is 15 and height is 20. So we have these three rates of change that we're dealing with. And we have at the point when the radius is 15 and the height is 20. So we now need a, if we want to draw a picture, we can. So we just have a basic cylinder. I'm not going to do it for this problem. But now we need an equation that's going to relate all of these things. Well, we're talking about the volume of a cylinder. So a cylinder is just a special type of prism with a base that is a circle. So if you don't know the volume formula for prisms, it's just whatever the base area is times the height. So we're going to do volume equals, the base area is a circle, so pi r squared times the height. So that's the volume formula for my cylinder. Now, before I differentiate, I want to ask myself, are any of these variables remaining constant? Because if they do, I can plug in the constant value at this point, and that will make my differentiation easier. Unfortunately, both the radius and the height are changing with time, and we're looking for the rate of change of the volume. So all three of these things are changing, so I'm going to keep them as constant values. So let's take the derivative of both sides with respect to time. So we have dv dt. We have a product rule on this right side. So I'm going to section off my left versus my right. So left, d right, the derivative of h with respect to h is 1, but then we have to apply chain rule on that, so dh dt, plus right, d left, so the derivative of pi r squared is 2 pi r, when it's with respect to r, but this is changing with time, so we must tack on a dr dt. So we're just going to clean this up a little bit. We have pi r squared dh dt plus 2 pi r h dr dt equals dv dt. And we are looking for the rate of change of the volume. So now I want to substitute in the values that I have. We have pi. We were looking at the point in time when the radius is 15. The rate of change with the height, it was decreasing by 8, so we're going to put in a -8, 2 pi r, 15 times 20. dr dt was +5 because that value is increasing. When I carry out this multiplication, so 15 squared is 225 times -8, so 225 times 2 is 450. So times 4 would get us to 900. So times 8 would get us to 1800. So -1800 pi for the first piece. And then when we do 2 times 30 times 20 is 600 times 5 is 3000 pi. When we add those two together, we get 1200 pi, and we're talking about a rate of change of volume. So make sure we pay attention to these answers. If we have multiple 1200 pi's, we want a rate of change with volume. So we want to make sure our label is whatever the quantity is cubed, so cubic inches per second in this case, so A. Electrical systems are governed by Ohm's law, which states that the voltage is equal to the current times the resistance. So they're actually giving us the equation in this problem, which is nice. So we don't have to come up with our own. If the current in an electrical system is decreasing at a rate of 3, I'm assuming that's amps per second, while the voltage remains constant at 12 volts, at what rate is the resistance increasing when the current is 28 amps? So what are we looking for? At what rate is the resistance increasing? So the resistance is R. The rate implies I'm looking for a derivative. So we want dr dt. That's what we're looking for. Now we know that the voltage remains constant. So that's going to be important. It stays at 12. That is not changing. We know that the current is decreasing at a rate of 3. So the rate of change of the current, and because it's decreasing, we put a -3. So we want to know when the current is 28. So when I is equal to 28, what's going on? So at that point in time. So here's our equation that relates all of these variables. Before I differentiate with respect to time, I know that voltage remains constant, so I'm going to plug in a 12. I'm going to take the derivative of both sides. Derivative constant goes to 0. On the right side, I have product rule, so left, d right. Derivative of r with respect to r is 1, and times dr dt, plus right, d left. Plug in what we have. The I at this point in time is 28. dr dt is what we're looking for. R, we don't have right now. But can we get it? Well, we know that voltage remains constant at 12, and we know at this point in time we have a current of 28, so we can solve for R using that equation, and we'll get R is equal to 12 over 28, which is equal to, if I divide both of those things by 4, we'll get 3/7. So 3/7, and then di dt is -3. So we're going to get -9/7, and I'm going to add it to the other side. So I'm going to get 9/7 equals 28 dr dt. Dividing by 28 is the same thing as multiplying by 1 over 28. So we're going to have 9/7 times 1 over 28. 7 times 28 is 140 plus 56, which is 196. So 196. And that's the only one. Yep, there is an answer here in ohms per second. Spherical balloon is inflated with helium at a rate of 90 pi cubic feet per minute. How fast is the balloon's radius increasing when the radius is 3 feet? So we have this balloon, it's a sphere. The volume, and I know it's volume because of the units applied to this 90 pi, so that volume is inflated at a rate of 90 pi cubic feet per minute. So I know the rate of change of volume. And it's being inflated, not deflated, so it's getting larger. So I know this is a positive number. How fast is the balloon's radius increasing? So how fast, that terminology indicates I'm looking for a rate of change. What rate of change am I looking for? Of the radius. So I'm looking for dr dt. And we know we're looking for this at the point in time when the radius is 3. So what's the formula that represents or relates all of these things? Well, we're dealing with a spherical balloon and its volume. So we're going to do volume equals 4/3 pi r cubed. Now, both volume and radius are changing, so we're going to leave those as variables, and we're ready to take the derivative. So we're going to have dv dt equals, we just have a nice power rule here, so we're going to get 4 pi r squared when we differentiate with respect to r, but tack on a dr dt to account for the chain rule when it changes with time. dv dt we know is 90 pi, that was given. We're looking at the point in time when the radius is 3, and dr dt is what we're solving for. Oh, that should be squared. So we're going to have 9 times 4, which is 36. So we're going to have 90 pi divided by 36 pi equals dr dt. So those pi's cancel, and 90 over 36 will get us 70 to 72 times 2, we have 18 left, so 2.5 feet per minute. So a radius is a linear measurement. It's a one-dimensional thing. It's a one-dimensional measure, so I just want a singular exponent value on that label. So we have feet per minute. So just in case you saw other 2.5 options, make sure we take that into account. Water is falling on a surface, wetting a circular area that is expanding at a rate of 8 millimeters squared per second. How fast is the radius of the wetted area expanding when the radius is 188 millimeters? Round approximations to 4 decimal places. So we have water falling on a surface, and this circular area is expanding. So we have this circle that's expanding out, which means its radius. So the area of the circle is solely dependent on the value of the radius. So the radius is getting longer. So how fast is the radius expanding? So how fast, again, it's an indication of a rate of change. We're looking for the rate of change of the radius. We're given the rate of change of the area, and I know that's area because it tells me, but also if it didn't, that label, that squared label indicates that we have rate of change of our area over time, and it's expanding, so I know the value is going to be positive. We want to know at what point in time, or how this is happening when the radius is 188. So what's the relationship between all these? Well, we're dealing with area of a circle. So area of a circle is pi r squared. Both area and radius are changing over time, so we leave them as variables. dA dt equals 2 pi r dr dt. dA dt we know is 8, 2 pi 188. dr dt is what we're looking for, so we will solve for this. Because the decimal format, we're going to use a calculator to determine what this value should be. And we should get C for the answer when you carry out the calculation of 8 over 2 pi 188. If we didn't have a calculator, we could clean this thing up a little bit. So we'll have 4 pi over 188. And 188 is divisible by 4, so we can go even further and say 1 over pi, that goes in 428, so 47. So 1 over 40, or 47 pi. And again, it's the rate of change of the radius, so we want a linear measurement. So C makes sense. An engine cylinder 16.1 centimeters deep is being bored such that the radius increases by 0.014 centimeters per minute. How fast is the volume of the cylinder changing when the diameter is 7.6 centimeters? How fast is the volume of the cylinder changing? So we know we're trying to look for dV dt. We know that the radius increases by 0.014, so the rate of change of the radius is a positive 0.014. We know the diameter is equal to 7.6. When it comes to the formula for the cylinder and its volume, diameter isn't present. We're going to need a radius, so we can divide by 2 here, and we'll get 3.8 for our radius measure at this point in time. So volume of a cylinder, again, cylinder is just like a special prism example. The base is a circle, so just area of the base times the height. That's how you get volume for prisms. So it's going to be pi r squared times h. At this point, we can differentiate, but actually, before I do, what I should have said is we also know the engine cylinder is 16.1 centimeters deep. So the height of this cylinder is 16.1, and that thing doesn't change. So how fast? So the radius is only increasing, that height is staying constant. So I'm going to substitute that value in right off the bat. So let's do that. So let's say 16.1 pi r squared. And that's going to make our life easier, because if I do recognize that, which I almost didn't, I would have to use a product rule on this, which at the end of the day isn't going to cause an issue, because I have to just recognize that the dH dt within my product rule is just 0, even though it's not explicitly given. You would have to recognize that it's not changing, so the rate of change of height is 0, and that would take care of that, but it's a lot more work, and therefore a lot more room for error. So if I identify remains constant and substitute before I differentiate, I just have an easier computation. So we're going to have 32.2 pi r dr dt. Rate of change of volume is what I'm trying to find, right? So all I have to do is substitute in for the radius at this point, which is 3.8, the rate of change of the radius, which is given, and that will result in B. And we plug that into our calculator. A container is the shape of an inverted right circular cone with a radius of 2 inches at the top and a height of 6 inches. At the instant when the water is in the container is 3 inches deep, the surface level is falling at a rate of negative 0.9 inches per second. Find the rate at which the water is being drained. So let's identify some of the numbers here and what they mean in the context of the problem. So in this case, I'm going to actually draw this right circular cone, and it's inverted, so it's it's pointing down. It says it has a radius of 2 inches at the top. So my radius here is equal to 2, and the height is 6. We have water in this container, and at this point in time, it's 3 inches deep, so it's halfway up. So I'm going to put H sub W for height of the water is 3. The surface level is falling at a rate of negative 0.9. So the surface level of this water is decreasing. So the water is being drained out of this cone. So what are we looking for when it's asking to find the rate at which the water is being drained? So we want this total volume of water that's being removed at that point in time. So we're looking for the rate of change in the volume of the water, the total amount of water in the cone. Now, what's the equation for this? We have, by the way, we should say the surface level is falling at a rate. So that means the height is decreasing. So this is the rate of change of the height. The surface level is going down, so that means my height is decreasing. So let's say dH dt, the height of the water at that point in time is going down by negative 0.9. Now, they were fortunate to give us a negative value, but the fact that if they didn't give you a negative value, you would have to recognize the fact that because it's falling, it would take on a negative number. So how do we relate everything? Well, we're dealing with volume in a cone, which is 1/3 pi r squared h. Before we differentiate, is anything remaining constant? Well, as the water drains, that circular cone that I have in blue, as that thing goes down or it slides down, the larger cone, the radius of that smaller cone within is going to shrink as well as the height. So everything's changing here. So I got to keep them as variables. So now, when I differentiate with respect to time, we have a product rule on the right side. So I'm going to section off left, and h is going to be my right. So left, d right, plus right, d left. dv dt is what we're looking for. Equals 1/3 pi. At the time when the radius is, we don't know. So we don't know what r is right now. But can we get it? We should be able to get it because we have this relationship that when r is 2, h is 6. So if I'm looking for r when h of the water is, or the height of the water is 3, I can set up a proportion to find that. So although they don't explicitly give me the radius of the water when the height of the water is 3, I can find it using proportional relationships here. So I can say when the radius is 2, the height is 6 of the larger cone, which means what will the radius be when the height is 3? It will be 1. dH dt we know is negative 0.9 plus the height given 3. 1 what's the rate of change of the radius? Well, that is not given to us. So there's a problem, because I have to find dv dt, and that is dependent on me knowing dr dt. So I do not know that. But we can go back. So if we run into this problem where I don't have a quantity, I may want to look to redefine my equation so that it's solely in terms of one variable. Because based on our ability to find what the radius is, using that proportional relationship, I should be able to define r as well in terms of height based on that. So the radius to the height is equal to 3 over 6, which means the radius can be redefined as 1/2 the height. And if I make that substitution into the equation to start, well, then I won't have a dr dt when I take the derivative. So why am I substituting for r as opposed to h? Because I have a dh dt, and I know that's going to pop up in my differentiation, so I can substitute in. But if I substitute in for r, or if I substitute in for h, that would leave me with a dr dt, and again, we don't have that. So we want to make a substitution so that when I take the derivative, I have everything I need. So we're going to clean this up before we differentiate. So squaring the 1/2 gets me 1/4, so I'm going to have 1/12 out here, pi, and then h squared times h is h cubed. Now when we differentiate, we just have a nice product rule over on the right side. So I don't even have to do, or sorry, power rule, not product rule. So we're going to have 1/4 pi h squared dh dt. 1/4 pi, at the time of the height is 3, and dh dt is negative 0.9. Plug that into our calculator, and we'll get C. So this is an example of using those proportions to find missing pieces. This is often a problem that trips a lot of students up because they go through that differentiation process and they find out that they don't have a value for R initially, and they don't have a rate of change of R in this case. We were able to find the value of R by setting up proportions, but we weren't able to find dr dt. So what we can do is go back and redefine the equation by substituting a quantity for r in terms of h, so that I strictly have a function in terms of the height. All right, a ladder is slipping down a vertical wall. If the ladder is 10 feet long at the top and is slipping at a constant rate of 3 feet per second, how fast is the bottom of the ladder moving along the ground when the bottom is 8 feet from the wall? So how fast is the bottom of the ladder moving? So when it comes to what we're looking for here, we may actually want to draw a picture to model this first. So let's say I have this wall, we have the ground, we have this ladder. So I clearly have a right triangle here. The ladder is 10 feet long. And then we have, it's slipping at the top at a constant rate of 3 feet per second. And then the bottom is 8 feet from the wall. So all I'm dealing with in this right triangle are the side lengths. So I don't care about the angle measurements. And therefore, if I'm relating 3 sides of a triangle, I'm going to be using Pythagorean theorem. So I'm going to write that right away. And let's label A, B, and C. So I labeled that first so that we could write what we're looking for in terms of how I label this. So we know that at the top it's slipping at a constant rate. So the rate of change of A, the length of the top of the ladder with respect, or the height of the top of the ladder with respect to its position relative to the ground, is represented by A. So as it's sliding down, the value of A is changing. So dA dt, the rate of change of the height above the ground, and now it's going down 3 feet per second. So this fact that it's slipping down, that means it's decreasing. So make sure you make that negative. How fast is the bottom of the ladder moving along the ground? So that's extending. So this would be moving down this way, which would cause the bottom of this ladder to extend out that way, which means dB dt which is what we're looking for, should be a positive number because it's increasing in length. That distance away from the wall is increasing, so it should be positive. So we might want to make a note of that. We have a ladder, it's 10 feet long. The ladder, as time moves forward, does not change in length, so it remains constant. And we're going to take that into account when we differentiate. Now, if we're going to differentiate here, we also know that at this point in time, the B value is 8. So it's currently 8 feet away from the wall. So let's differentiate with respect to time. Both A and B are changing over the course of time. The C value, the length of the ladder, remains constant. So if I were to plug in a constant there and differentiate, it would go to 0. We don't have a value for A at this point in time, but knowing at this point in time that B is 8 and C always remains 10, I can use Pythagorean theorem to find out that A would be 6. dA dt, we know it's going down by 3 inches or 3 feet per second. 8 dB dt is what we're looking for. So I can say that's negative 18, negative 32, so 16 dB dt equals 32. So dB dt, oh, where's my error here? 36, sorry, not 32. Is going to be whatever 36 divided by 16 is. And when we use our calculator to compute that, we'll get 2.3. That ended up being a positive value, which it should be, because the length of B is increasing over the course of time. So 2 more. Rectangular swimming pool, 16 by 11, is being filled by 0.4 cubic meters per minute. How fast is the height of the water rising? So what we're looking for here is pretty obvious, the HDT. We want to know how the height's changing over the course of time. It's being filled up as a volume. And we have a rectangular swimming pool, so volume for a rectangular prism, length times width times height. dV dt is given at, I'll write it over here. It's being filled, so the volume is increasing, so it's going to be a positive value. If it was being removed, we would want to make that negative. So again, make sure you're paying attention to that. We know that the length is equal to 16 and the width is equal to 11. And as you fill a pool, the length and width of the pool are going to remain constant. So that's nice because we can fill in those values before we differentiate. So when we take so 16 times 11, so 16 times 10 is 160 plus another 16 is 176. So differentiating. So whatever 0.4 divided by 176 is the rate of change of the height. And that's going to be a pretty small number. And there it is. And again, the height, if we're filling the pool, the height of the water should be going up, and therefore my height should be positive. So that's what I mean by interpreting your solution as well, is make sure your solution makes sense in the context of the problem. The height should be increasing, so the rate of change of the height should be positive. And last problem, man flies a kite at a height of 50 meters. So we have some kite. 50 meters high. The wind carries the height horizontally away from him at a rate of 10 meters per second. So as this thing's blowing in the wind, the rate of change of the horizontal distance between him and the height, so it looks like we're going to have a right triangle again. And are we just dealing with size because it says the kite changing when the kite is 130 meters away from him. So we know this is 130. So yes, we're going to have all side relationships in a right triangle. So we're going to be dealing with Pythagorean theorem again. So let's label these A, B, and C. We want to know how fast is the distance between the man and the kite changing. So we're looking for the actual distance between them. So distance between 2 points, a straight line that connects them. So it's going to be our c value. We want dc dt. That's what we're looking for. We know that at that point in time, we're looking for when this equals 130. We want to know how fast that's changing. This thing's going to be 50 feet high, and it carries him horizontally away at a rate of 10 meters per second. So it's moving away from him. So the horizontal distance is increasing. So the rate of change of A, the rate of change of that horizontal distance, because it's growing in length, is a positive value. dB dt, it looks like the height's going to remain constant in this problem. So our dB dt is 0. So we can plug in a constant value before our differentiation. A changes, of course. And c is obviously changing as it moves away. So c representing the distance between him and the kite. So when we differentiate with respect to time, plus 0 equals 2c dc dt. dc dt is what we're looking for. Do we have an a right now? We don't, but again, at this point in time, we're given 2 of the 3 sides, so we can use Pythagorean theorem to find the third, and we should get 12. Not 12, 120. Sorry. So we're going to do 2 times 120. The ADT is 10. Equals 2. At this point in time, the C is 130. dC dt. So if we divide both sides by 260, we're going to get 2400 over 260. And we make that computation. It should be a little less than 10. If I eliminate this, so if it was 260 over 26, it'd be 10, so it's a little less than 10. So the only one that makes sense is this if we didn't have a calculator. And again, if this is blowing away from this person, it would make sense that the distance between them is increasing, so our rate of change should be positive. So if you saw a negative 9.2 and a positive 9.2, interpreting the problem and how this thing is unfolding would allow you to select the positive, and taking into account signs from the very beginning, when we actually do the math, we get a positive number anyway. So those are 9 examples for related rates along with strategy.